All right, welcome back. Today we're going to have a lecture on this thing called a support vector machine, or SVM. Professor Wu. So let's get started. So, support vector machine, SVM. It was one of the most famous early classification algorithms. The idea is pretty easy to understand, and the predictions are really accurate. So it did a really good job, especially when we do this thing called the kernelization. So, support vector machine was invented by Dr. Vapnik. It has a very beautiful theoretical background, and there are many versions of it. Today, we're going to learn there's the linearly separable soft margin classifier. We're going to focus on these two, and I will leave the nonlinear boundary classifier for advanced machine learning classes. Okay, so in this case, we're going to focus on two basic versions shown here and here, right? So there's the linearly separable ones. So these two versions are based on the idea of picking the line with the largest margin. You see, if we're trying to identify, let's say these are 1 and 0, we're trying to essentially identify the line that separates the two groups of data. Before we move on, we need to basically have some review of basic mathematics, such as linear projection. To understand SVM, we need to first know what a unit vector is. Hopefully, you already know what it is and that this is just a review. How do you get a unit vector? And then what is a projection? So, for example, given the point C, like if we want to cast a shadow down onto the v vector, do we are we able to find a distance, this distance right here, right? Are we able to then identify this point D? These are the things that we need to review. So let's start with the concept of a unit vector. A unit vector is simply a vector of length 2. And so right here, this is not a unit vector because the length is not equal to 1. So this right here is a length 1. You can see this is also length 1. So any vector that has a length. So how do we go about measuring the length? Right over here is very obvious that the length is just 1. But what about this? Right, the way we measure the length is to what we call the L2 norm. If you calculate the L2 norm, that gives you the length of a vector, and you want the L2 norm to be equal to 1. And when that's the case, we know that what we have is called a unit vector. Now, when a vector is not a unit vector, we can calculate the length by calculating the L2 norm. So this is 3, 4. So it's 3, 4. So we know the length here is 5. Now, all we have to do is take the vector and divide by the length, and we'll get a unit vector. So for example, this vector is 3 and 4. If we just divide by the length, this now has a length of 1. Let's test it out. If we were to take the L2 norm of this, we'll take the first one square, second one square, and the square root. Notice now the vector is length 1. So if we have a vector that is not your unit vector, you can always convert the vector into a unit vector by dividing the vector by its length. Okay? Now, once you divide the resulting vector would be then of size 1. This process of taking a vector and moving it to length 1 is called a normalization. And when a vector is normalized, v, what we like to denote that vector as v hat. So v, you can think of that as a vector. And then when we want to normalize that vector, v hat is what we denote as a result of normalization. Okay, so right now, let's do a quick exercise. Given this vector, you want to pause the video and see if you can find a unit vector. Okay, and once you find a unit vector, v hat, you want to make sure and check that v hat, the L2 norm, is actually equal to 1. Okay? So the idea of unit vector is just a vector of length 1. Okay, pause the video and we're going to move on. Okay, so now that you have a better idea of what a unit vector is, given a point C, we have this vector here at C. if we want to draw a perpendicular line from C to U, we want to draw a perpendicular line, right? Kind of form a triangle. What is the distance from this 0 to D? Like, what is this distance when we draw a line below? Well, it turns out that the equation for this distance is really easy. If this is U and this is V, the distance is simply V times U hat. So U hat here implies is unit vector. So if we just convert U into a unit vector, and then do the dot product of V, that will automatically give us the distance here. Okay, so the distance from here to here could be calculated. And see if we can get the same distance. So this right here was this right here was 4, 2, right? So notice how U is 4, 2, 4, 2. Now we want to find U hat, so we take 4, 2 divided by the length. Okay, so the length is, remember, 4 square plus 2 square. Right, so that's how I got the square root of 20. So now we have U hat, and if we just take the U hat and dot with V, we just take the dot, that gives us the distance, results to be 3.13. Take a look, right? So what it's saying is that the distance from here to here, this distance here, is roughly 3.13, right? So if 3 is here, it makes sense that this is 3.13. So that's the distance. You can calculate the exact distance this way. So that is called projection. Basically, we take one vector, draw a line to another vector, and we figure out the distance after you draw like a projection. Now the next thing we want to do, if we know the distance from here to here, are we able to find this exact point? And the answer is yes. We can find that point. Now, it's actually quite simple. We know the vector u, and we know the unit vector u hat. So if u hat is length 1, and we know the length is some value, I think is 3.13. So we simply multiply 3.13, the distance, total distance, by u hat. And that will give us the final location. So remember, u hat was this. So if we just take u hat multiplied by 3.13, right? So this is u hat, and we multiply by 3.13, we got the final result. Now notice it's 2.8 by 1.4. That is the point of D. Let's see if it's right. 2.8, right, and 1.4. So this tells us that if we are drawing a line, right, and we're performing some kind of a projection, which is, you can kind of picture that there's a sun and it's casting a shadow. We can figure out the size of the shadow as well as the exact location of the threshold. So that's the general idea, right? So before we move on, let's do a quick practice. Now we have two vectors, u and v, right? So what your next practice is to figure out what is this D point, okay? Given that we know u and v, what is the distance from 0 to D? And then given a vector D as the vector from 0 to D, what is the norm? So this is a D. What is the L2 norm of D? Okay. So you want to pause the video, make sure you can do this. You can use Python. Okay. So I think if you want to go back to the video a couple times to make sure you understand these concepts, because we're going to be using them for the actual algorithm itself. The algorithm, and in the simplest form of support vector machine, is the assumption that we basically have two categories. We'll call this the blue category 1 and the red category 0, right? Or actually, we like to do 1 and negative 1. 1 and negative 1. So the idea is, what if we can find a line that separates them And therefore, we know whatever's above the line belongs to category 1, and whatever's below the line belongs to category -1. And then that essentially will allow us to perform classification. So what we do is we identify equation of a line, right? That separates two classes. So equation of a line looks like this. You can also write it this way. But for this class, we're going to focus this version of equation of a line, which means it doesn't matter what x1, x2 you plug in. You all those points are going to be 0. Okay? So 0, when you plug any x along the line, it's going to be along the line, right? Now, if you plug any x1, x2 that's in the blue, well, that's above the line. Therefore, this value will be greater than 0, so positive. In contrast, if we plug any points like red that's below the line, then this is going to be below 0. So by having a line, looking at if the point is above the line or below the line, we can essentially identify whether that point belongs to 1 or -1. Okay. So on the right, so this is the line equation of a line, but we can simplify it where I let w equals a vector, x equals a vector. Okay. Once you have that, the equation of a line can be compactly written this way, even if you have high dimension. Like right now, we only have x1, x2, so that's 2 dimension. But you can imagine you end up having higher dimensions, and we can contain the higher dimension if we have x1, x2, x3, x4, x5, and we can rewrite it into just a simplified equation of a line. Okay, so imagine we have this equation of a line, and we know what w is, right? Let's say we know w, and the way it will work is that if we know w, we can plug any point into this equation, and if the result is greater than 0, it means that the point we plug in is above the line, right? And if the point of this, if it's below 0, right? If we plug any point in and the result is below 0, it means that it's below the green line. The goal of SVM is basically to identify W and B. Like if we can identify W and B here, then anytime we plug X in, we just have to check whether it's a positive value or negative value, which is the sign, right? So if it's positive, it means it's above the line, then we'll assign that to 1. If it's negative, therefore sign will give you a -1, then we assign that to a -1 value. So that's basically the idea. We want to find a line and then categorize a point to see whether it's above the line or below the line. And in order for us to do that, we need to know W and we need to know B. Okay, so let's continue. Line scaling. So one interesting thing about a line is that if you multiply the line by a number, any number, you're just making you result in the same line. Okay, so for example, this is the equation of this line. Okay, now if you multiply this equation of a line by any number, let's say we multiply it by 2, the result, if you plot it out, is still the same line. So multiplying by a line by a constant doesn't change the result. And therefore, when we multiply the equation of a line by any constant, whatever is positive, which is above the line, will stay above the line. Whatever is below the line will stay negative. Therefore, the magnitude of the line doesn't matter. Okay, you can scale the line to anything, and it will not matter because multiplying a number by a line implies that you have the same line. You don't get a different line. So at this point, this is an important concept you need to understand. Therefore, I think it would make sense for you to pause, think about what we just talked about. So what you want to do is you want to pick any blue point. So these blue points and plug it into the equation. This equation here is the equation of the green line. All right, that's the separator. So you can imagine if you pick any blue point, or anywhere with above the line and plug it in here, you're going to get a positive value. So you want to pause, check that that is true. And then if you plug any red point into the equation, it's below, you should get a negative value. And that's important. You need to like understand that you're going to get a positive or negative depending on if it's above or below the line. And after that, you want to then plug it into a constant 2 times the line, right? And you will see that it doesn't matter, that you can multiply in, plug any point that was above the line. If you have 2 times the equation, it stays the same. It's still above the line. And then after that, you can pick any point along the line. So if you pick any point along the line and then plug it into this equation, if it's along the line, it's not above and it's not below. Therefore, you should get a 0. So plug these numbers in, like try to understand what I mean, that a point above the line will give you positive, a point below the line, it will give you negative, and that scaling the line doesn't matter. Okay. If you pause and do this exercise, you will understand that the magnitude of the line doesn't matter at all because you can multiply by the constant. And this is a very key concept you need to understand now because it's going to come up later, that understanding that stretching a line longer, it's still the same line. That's just a very key concept you need to understand geometrically. Okay, so the idea is pretty simple. We want to find a line that separates the two groups, right? Group one, group two. However, there are infinite possible choices of a line, right? This is a line, that's a line, that's a line. So you can pick any line. And some of the lines will give you a good choice, and some will give you bad. So these two are bad choices. If you try to separate the two group this way, right, that's not a good idea. And this is a much better idea because then you are separating the two groups well. Okay, so how do we go about picking the best green line? Well, there's the first step is to get these two key logic. Logic number one, right? Remember, our classification labels in this particular case for y, for every sample, is 1, 1, and -1. Okay, that's the very first logic. You just need to remember, okay, our labels, y1, y2, they're equal to 1 or -1. Whereas when we're doing logistic regression, it was 1 and 0, right? So we just changed the labels. And we made it so that it's -1 for red, and -1, and 1 is for blue. So the 1 is here above and -1. Okay, hopefully you can hold that in your head. Next, the next logic you need to understand is that, remember, when you plug the x value in, any point you plug in, if it's greater than 0, that means it's above the line. And if it's negative, any point negative, it means it's below the line. So any point plugged into this line equation tells you if it's above, if it's below. So blue class is above, red class is below. Okay? Now, let's combine these two logic 1 and logic 2 together. If we follow logic 1 and logic 2, it means that if we multiply the label, which is 1 or -1, by the blue, which is always going to be a positive value. So blue is supposed to be a positive, and the label for blue is supposed to be +1. So if we multiply 1 by a positive value, that will always give us a positive value. In contrast, if it's red, then the label is going to be -1. And whenever we put a point in, if it's part of the red, this right here should be a negative value. This implies that we have a negative value times a negative value, giving us positive value. Okay, so if we correctly labeled it, then this part should be positive when this part is positive. And this part should be negative when this part is negative. Right? So this is the key insight. If we correctly classify it, It doesn't matter if it's blue point or red point. We always want this number to be positive. So in a way that when this is positive, then then we got a correct classification. So we conclude that basically we can use this as a way of evaluating the correctness. So if it's positive, then it's correct. Then we want as positive as possible, right? So this leads us to an optimization equation. We want this, which is here, for every single sample. So there are n samples. We want for n samples, if it's correctly done, this will be positive. So we want all n samples to be correct, right? This implies that we want to find a W, the weights, such that the correctness is maximized. So this equation is basically just a way to figure out if it's correct or not, right? So this is maximizing the correctness of the labels. Well, that's a very good start. So doing this is a good start. However, that's not good enough. That's not good enough. Notice how if we were to maximize the correctness, there are many possibilities that are all correct. Notice how any of these lines, they perfectly separate blue and red really well. So there are infinite ways to draw a line that separates them. Is there one particular way that is best? Right, better than all the rest. Like you don't want to have infinite solutions. Is there one solution among the infinite that is as good as it gets? And the way they figure this out is that they can use an additional criteria. Right, instead of picking any line that perfectly separate the blue and the red, we want to pick the line that give us the largest margins. So over here, for example, we could draw the line this way. But notice how we don't have a lot of margin for error. So what we want to do is we want to draw a line such that this margin, right? I'm going to define the points closest to the margin as support vectors. So we want the margin from the middle to the support vectors, these are margins, to be as large as possible. Right. Once again, notice how if I drew the line this way, there's very little margin for error. Right. So, but if we draw it this way, notice how the margin is much larger. So by having a largest margin for error, we determine that as the optimal solution. So, so now the key is then how do we go about calculating the margin? Right? Because we want to maximize the margin. So we want to maximize correctness, which is what we did previously. And now we want to maximize the margin. How do you mathematically define the margin? Okay. Here, first, to understand the margin, we need to first understand that for this equation, this is the equation of a line, right? That's the equation of a line. When we have this equation, the W vector, this W portion, is also vector. And this vector is always perpendicular to the line. So if this right here is the line, the W vector is the perpendicular component. And this is always true. This is just a geometric property of a line. Okay. So So crucially, this line, therefore, notice how this line is parallel to the margin. So this is the same line, like pointing in the exact same direction because they're parallel. All right. So this, like, you have to understand a lot of things simultaneously. So before we move on, let's try to convince you of this again. Pause the video and look at this line. This is the line that we have. Um, I want you to draw this line. And then after you draw this line, draw the W vector. And you should see that this line and the W vector are perpendicular to each other. Like understanding this perpendicular is key. Right. Now, if you pick any random point and draw the shortest line, D, from the point to the line. So if you pick pick a random point, like here, and if you draw the shortest line, then you will see that this any point will be parallel to W. Okay, one more time. So if you pick any point and you draw a perpendicular line, you will see that it will be perpendicular to W. Okay, not perpendicular, sorry, parallel to W. So okay, so pause the video again, try to convince yourself this fact, and then we'll go on. All right. Now, if you understood what we went over last time, then we're ready to mathematically define the margin. Okay, so let's define this point as a support vector, and therefore this right here is the margin, right? The distance here is the margin. So we have this point xp. So if we take xp plus d, then it will result in this vector. We take this vector plus this vector will give us this vector. So we'll start with that equation. So we know xp plus d is equal to x hat. xp plus d is equal to x hat. And then we rearrange a little bit. That means xp is equal to x hat minus d. So xp is x hat minus d. Since d is parallel to w, we can say that d is simply some constant alpha. We don't know what alpha is right now, times w. So we have w, and if we have some number alpha times w, then we have this d, right? So now, given this equation, I have this expression of d. I'm going to plug it in. So xp is equal to x hat minus alpha w. Okay. Okay. So we know that xp is on the line. It implies that if we plug xp into the line equation, so we plug xp into the line equation, we should get 0. So we know this is true. And now if we plug in what xp was defined, see, we just defined xp here. We plug xp into this equation, we now get this expression. This expression here has only one unknown, which is alpha. So we can solve for alpha. Once we solve for alpha, we now have an expression of alpha, and we can plug alpha back here. So this now give us the term d, right? Now we know what this vector is, d. Okay, where d is equal to alpha w, so this is alpha times w. Okay, finding the magnitude of the margin. So now that we know d, which is a vector, we don't want the vector. We want to know the distance, actual length itself. So what we do is we take d and calculate the L2 norm. L2 norm. So the L2 norm now is d times d square root, and we plug d in, which d was defined here. We plug d in, and now we basically know what alpha is, right? We figure out what alpha was. So we just plug alpha square times w transpose. Now, the math here, you want to take a second and stare at this for a bit. This right here, once you multiply this out, then notice how w transpose cancel each other out, and this just becomes square. So if you take the square root of this, it's simply the L2 norm. And if you take the square root of this, you'll get the absolute value of this. So this is the magnitude of the line. So here, the key you want to remember is that we are trying to find this magnitude, right? So this right here is a mathematical representation of the margin. And what do we want to do? We want to maximize the margin. So what we have now is we are trying to maximize the margin. That's the equation of the margin. And this right here is the equation for correctness. So now we want to find a W that maximizes the margin and maximize correctness. So we have two equations we're simultaneously trying to maximize. Okay. Now, if you remember from the very beginning of the class, I said that if you multiply any constant by a line, you get the exact same line. So if you can get the exact same line, it implies that the magnitude of the line doesn't matter. So over here in this maximization, this is the magnitude. So you can pick any number for the magnitude and you'll still have the same line. And therefore, we simplify this simply by picking the magnitude as 1. Okay? So you what we are saying is by maximizing this is equivalent finding the W that maximizes this. So these two are equivalent. Okay. All right. So now we have a simplified version that we want to solve. So first we have maximization of the correctness, and then we have maximization of the margins, which I showed you. Here's the reason. And when you're trying to maximize the margins, it's equivalent to minimizing 1 over the margin. Okay, so we're trying to maximize this, and we're trying to minimize the inverse of the margin. When we combine these two objectives together, right, we combine them together, notice we're trying to minimize this, so we're minimizing this. And now we're also minimizing the negative of the negative correctness. I add the lambda so you can have finer control of how much emphasis you want to put it on the correctness. And that's it. This right here is the most basic form of support vector machine. If you solve for W by taking the gradient descent method, then this problem will be solved. You would essentially be able to find this line. Now, how we got this equation. There's a lot of step involved. So it's if you want to truly understand it, you will need to go through the steps over and over again to see how we got this equation. Okay. So after you have this, we've done this many times. We simply have to find a derivative and the problem is solved. Okay. So finding the support vectors B. So over here, we just basically figure out the objective we need to minimize in order to find W. So now let's assume that we found W. Then we still need to know B, right? If we know W, we still don't know B. So how do we go about finding B? Because when we take the derivative, the B actually cancels out. So there is no B. You're just only finding W. Well, finding B is actually pretty easy. If we know this portion, that means we can take every single point and project onto W. So what's happening there? For every single point, notice we can project onto W. So we got this point, this point, this point. So we got this point, this point, this point. And when we perform projection, we know the distance. We know the distance to here. We know the distance to here. We know the distance to here. So what are the distances? 0. 0.4, 0. 0.5. So and 0.8. So this right here is 0. 0.4. This right here is 0. 0.5. And this distance right here is 0. 0.8 here to here. So we know the distance. We also know all the distance for the other class, which is 4.1, 4.4, 4.8. So the distance is from here to here, 4.1. From here to here, 4.4, was it? And then from here to here is 4.8. So if this is the case, we know all the distances, then we also know the center point. The center point must be between 0.8 and 4.1, right? It must be somewhere in between these two. In fact, it's the center point. So if you just do 4.1 plus 0.8 divided by 2, which will give you the center point, that center point is your B, right? So if we take this 2 center point, it turns out that the center point is at 2.4. So if you put this value as 2.4, 2.45, notice how all the values on subtract 2.45 is positive, giving us label of 1. And if we have all the negative values and subtract 2.45, it gives us a negative value, resulting in the class of -1. So this is how essentially you get the b value. You project, you essentially project all the points onto W, and then figure out the support vectors, the ones going here and the ones going here. And then the middle point between the support vector is your b value. Okay. All right. So SVM can be solved with gradient descent. Okay. So take a moment. This is our objective. Take a moment and find a derivative for the SVM objective. Once you find the derivative, then you want to put it in a compact vector form. Pause the video so that you can make sure you do that. So over here is the answer for the derivative. An L2 norm square is just 2W. Hopefully you remember that. And this right here, when you take the derivative, this is a constant value. So it's a vector times vector, right? So the result is just y, and then w goes away with x. So that's what happens when you take the derivative. So this right here is the derivative. Now, this is a number multiplied by vector. Therefore, we can split it into a dot product, x1, y1 times x1, y2 times x2, right? And then when you do the dot product, it will perform the summation. This implies that this is just x transpose and this is the y. So the derivative turns out to be really, really easy for you to find. Now, once you have the derivative, you project, you can normalize w and project all your x's onto w. That's how you find a margin. So you find a margin, you find a point in the middle, that's b, and the problem is then solved. So that's the general idea of SVM, where you are trying to you have an equation where you're trying to maximize the correctness of your labels, maximize the correctness, while maximizing also the margin, which is minimizing the inverse of the margin. Okay. All right. So here's the code that implements this. Notice how this is a derivative. I define a derivative here. And after that, I just run gradient descent. And the problem is basically solved. Now, here's the result of the code. And let me show you what's happening when we run gradient descent every single step along the way. So when we run gradient descent on SVM, this right here is notice how the green line is the W vector, and it's perpendicular to the green line is the line separator. And notice as we run gradient descent, the perpendicular line of the green line is creating like a large separation for the margin. Okay. Okay. All right. So let's continue. Now, what we learned so far is the most basic form of support vector machine, which looks like this. So as I reiterate, this part you're trying to maximize the correctness, and this part you're trying to maximize the margin. Now, the there's a lot of room for improvement, and that's how the other algorithms come about. Now, if we get the correct prediction, remember, if we get the correct prediction, then this is going to be a positive value. And because of this negative, a correct prediction will give us a positive times negative, then we're going to have a negative result here, which is good because we're trying to minimize, right? We're trying to minimize, therefore we want this to be as negative as possible. But do we? No. We don't necessarily want to large negative value, right? Because if we already have a correct prediction, so if this is already correct, making this more negative is not preferred. Like it doesn't really help. If it's already correct, then it's good enough. So more negative values in this objective will be preferred. It's saying that we want this to be as negative as possible, even though as soon as it's negative, it's already correct. So that's not like matching the reality of what we want. And as a result, we can improve this so that we only penalize objective if we got the wrong prediction. Okay, so this goes back to penalties. So now by adding RALU, this means that if we got a negative value, then it's correct. RALU will simply wipe it out and say it's already correct. I'm not going to deal with it. However, if this is positive, then we have a problem because RALU is just going to keep the positive value. Therefore, whenever there's a mistake, this objective will then try to minimize it. And then when it doesn't have a mistake, then it doesn't minimize. Okay. So the penalty only exists when we got the wrong prediction. Okay. So let's continue. Now, so this is the origin of the second form of SVM, but this is not the one you will see. There's more assumption that is built in, okay, to the one that you will see when you type into Wikipedia. So we went through the easiest one. Now we went through the second one. Now let's add even more assumption into the objective. Right now we're assuming that all the samples are correctly labeled, but sometimes they're not correctly labeled. That the label itself can be wrong. So let's look at this x. This value, because it's below the line, then it's going to say it's part of red. However, because it's so close, there's a chance that this was just wrongly labeled. So if this is not correctly labeled, then we have a problem. Okay. So what if this was actually blue instead of red? So this kind of mislabeling happens a lot in life, and it will completely screw up the learning process. Therefore, in order to compensate for minor screw ups, what we do is that we don't ignore the label if it's already correct. Okay. If we get the correct label, previously Ralu is going to say, let's ignore it. Now, we're going to add an extra term t. How does this t help you? Well, think about it. If it's negative, let's say is negative 0.1, then with Ralu, it will just ignore it. Okay. But what if we set t to be 1? Which means that 0.1 will still cause a penalty because 1 minus 0.1 is a positive value. So basically adding the t value give you an extra bit of margin. So if it's only a little bit correct, you're still going to look at them. If it's really correct, that's when you ignore. That's the impact of adding this t. And this version of SVM is the most common version you will see from Wikipedia. This is how the equation came about. Okay? And this t value for SVM, most of the time we just pick the number 1. And this is called a soft margin SVM. And over here, you guys know how to take derivative of ReLU. You take the derivative, and the problem is solved. All right. So if you want to learn run the soft margin SVM, it's actually the standard one in sklearn. Like when you run SVM predict, the equation they use is the one I just taught you. All right. So let's start with the simpler version. So the version 1 with the hard margin, which we calculate the derivative. I want you to see if you can write this algorithm yourself and separate these two classes. Okay. All right. Now, I understand the SVM algorithm is hard. SVM algorithm requires you to simultaneously hold a lot of concept in your head in order to understand. So the part that you want to go over is to understand that basically you're trying to find this line. And the way you will pick this line is to maximize the correctness of your prediction and the margin, and the rest is detail of how we end up doing that. Okay, so that's it for today. I will see you guys in the next lecture.